Okay, welcome back to Calculus 2. Here we have the integral of dx over x times the square root of x squared minus 1. And even though it says it's in the trigonometric substitutions, I'm still looking at this as a square root of a square kind of a problem. Now, thinking like, well, if the x was up here, then we could make this a u substitution, and it wouldn't be a problem. But the x is in the denominator, so if I make my u to be x squared, I'm going to end up with a du of 2x. I'm going to have to figure out a way to make that 2 over x. That's not going to work out so well. So we're still looking at triangles here. So I'm going to go ahead and draw my triangle. In this case, we got a squared plus b squared is equal to c squared, just to remind myself of Pythagoras. And we could say something like b squared is equal to c squared minus a squared. Now I'm looking at this x squared minus 1 and this c squared minus a squared. I'm thinking, oh, wait a minute. This is the same shape. My c had better be x. So we could say this to be x. And then I have to pick one to be a 1 here. I'm going to go ahead and pick the adjacent side to be 1 so that my opposite side is going to be c squared, right? So we have x squared minus 1 squared is equal to c squared. So c is just equal to the square root of x squared minus 1. Okay, or b rather. It's going to be x squared minus 1. So we have x squared minus 1 here, okay? And be able to figure out what's going on with this. Okay, so if it helps, you can always go back to Pythagoras and kind of make sure it works this way. Here's my theta, and then we'll figure out what we have from here. Okay, so with this substitution, we're going to say we have a hypotenuse over an adjacent. Pretty much you have three different substitutions. You'll be looking for a sine theta, you're looking for a tangent of theta, or you're looking for a secant of theta. Why secant? Is because when you take the derivatives, we're going to have positive derivatives. So the derivative of sine is going to be cosine. Derivative of tangent, secant squared. Derivative of secant is going to be secant tangent. Okay, so there's reasons as to why we set them up with these particular three. If you said, oh, we want cosine, we'll take the derivative of cosine, we get negative sine. Take the derivative of cotangent, we're going to get negative cosecant. You take the derivative of cosecant, you're going to get negative cosecant cotangent. Okay, so it's just because we don't want the negative signs. And that's why we go ahead and set them up so they're this way, because it's already a complicated problem. And it's just easier if we don't end up putting new negative signs in here. So we're going to say that secant of theta is equal to x over 1. Okay, and we're going to set that up because we want x is equal to secant theta or anything else. So we go ahead and take our differential, we're going to be able to get easy problems. So I'm going to say secant theta, tangent theta, d theta, all right? So that's my dx, right? And now we're going to figure out what we're going to do with the rest of this stuff. So I'm going to rewrite my integral. I'm just going to break it into its component pieces here. So we have our dx times, and then what do we have here? We have a 1 over x, okay, 1 over x times a 1 over the square root of x squared minus 1. So I can go back up to my triangle and figure out what am I dealing with exactly. So 1 over x, that's adjacent over hypotenuse. That's a cosine, okay? So we have a cosine theta here. There's no limits, so we don't have to worry about that. We have a 1 over x squared minus 1. That's going to be adjacent over opposite. That's going to be a cosine or cotangent, right? Adjacent over opposite. It's cotangent. So we're going to have cotangent of theta. Okay. And then my dx, I'm going to write that at the end. So we can say our dx hops over here a little bit. Okay. And my dx was secant theta tangent theta. Secant theta tangent theta d theta. We're still integrating all of this. And now we're going to do some magic with the trig and see what's going to happen. So we have the integral of cosine of theta times cotangent of theta times 1 over cosine, that's my secant, right? Times tangent of theta, d theta. Well, cosine over cosine, that's 1. Cotangent times tangent, that's 1. So pretty much I've got to integrate d theta. That's a physics integral. I love those integrals. Okay. And physicists, you'll see this when you take physics too. The physicists go through a lot of pain, a lot of gymnastics, mathematical gymnastics, in order to be able to integrate the easiest thing in the world. Like, why? We learned all the fancy integration techniques. Yeah, they did too. It's just been a long time for them. So if they can minimize the amount of calculus they have to do, they will do so. So I'm not going to complain. Integrating d theta, thanks. That's an easy problem. That's going to give me a theta plus c. Okay. Now we have to go back up to our triangles. And what the heck was theta? Well, we have secant of theta is equal to x. So theta is going to be the inverse secant of x. And that's how we're going to write this thing. Fortunately, this is an indefinite integral. So we have secant inverse of x plus c. And that's pretty much what you got with this problem. That's what we're done. Okay, if it was a definite integral, it would be a little bit harder because we have to, there is no inverse secant on my calculator, so I'd have to do the reciprocal and deal with it that way. But fortunately, this is an indefinite integral, and there we go. Okay, a lot of these problems turn out to be kind of nice and sweet. They can get kind of hairy too, but one of the reasons we want to do this is that if you end up with like integrating d theta, and where did that go wrong? Because this is deceptively too easy. Okay, but in this case, I get these problems out of textbooks. They're, of course, they're going to work out nicely. So I'm going to say thank you very much for watching the video. I'll see you in the next one, and take care until then.